Here's video help for problem 5 of lecture 32. It may be a little bit hard for you to read, off the video here, but you've got this sheet in your lecture notes, so you'll know exactly what I'm referring to in each case. Problem 1. Again, I'm going to tell you things that I love telling you. I think they're worthwhile having you here, but I'll try not to wreck the problem. Problem 1, make sure you know how to relate the velocity to the position r for circular orbits and, for example, for escape, an escape orbit. Problem 2, this attacks one of the famous problems. Remember that an FBD only put the forces in contact or the forces that reach in like gravity. And later you'll learn about electrical and magnetic forces officially in the next semester. Number 3, attack another famous problem. We do not have an equation for the static friction. We don't have an equation for static friction. Number 4, thanks to our demos, we know how to do this. I think people really know, thanks to you guys doing such a wonderful job with demos, that this problem connects well with that. Problem 5, if I call this tension, in other words, I'm thinking about this pulling on the mass and the mass pulling back on the rod, investigate this with your second law radially. And you may find that when you put in all of the appropriate parameters and conditions, that you get T is negative. So that means that in fact you're pushing, that's compression. And so that's okay. So if it's pushing on the mass is pushing back on it. Question is, think about, tension being negative, T being negative, in which case it's compression and vice versa. Problem 6. We learned when we had one dimension elastic collisions, we could get rid of that quadratic kinetic energy conservation equation and reduce it to, do you remember, the relative velocity V1 minus V2 is a relative velocity of V1 relative to V2. Is the negative of the relative velocity of those same two bodies, parts, masses afterwards. That was what we got as a master equation. Number 7, you remember that when we're talking especially about a rod, we had a general acceleration could be, decomposed into a radial part and a tangential part. Tangential. And of course, this may be pointed in this direction. I'm just writing this generally. Which one of these refers to centripetal? Which one of these refers to alpha? Which one is connected with alphas? And also, you know how to write, when you're talking about centripetal acceleration, you know how to rewrite this in terms of omega, right? In terms of omega, how do you rewrite V squared over R? For the second page, if you're given alpha and given omega, then the question is, can you figure out the ratio of the total kinetic energy to the magnitude of the net torque? The thing I want to tell you is that typically in multiple choice problems like this, multiple choice, there might be something that looks right, but is it completely generally always right? And in fact, is there another answer that's absolutely always right? Number 9, when you're looking at torques, in this particular case, N sub W is the normal force from the wall. Then, let's look at this term. Minus NWL sine theta. NWL and that is theta. That's the correct torque then around this point, and with a minus sign, that's clockwise. And now the question is this then an appropriate torque around that point? And so forth. You can go on to look at all of these. In number 10, I really have to bite my tongue because as soon as you start thinking about, center of mass, there's only one answer here that really fits. One thing, let me just tell you that if you had an expression for, center of mass, like x center mass, then the velocity in the x direction, center of mass, is just the derivative of that, by the way. Number 11. Oh, we're going at constant speed. First thing that tells you is that the work being done at any time, the net work is 0. I've got acceleration 0 and the net force is 0. And the power, this is my chance to just tell you this. Like we were doing for torque, the torque equation on yesterday, we had power is actually the net force really dotted into the velocity. And that can be rewritten, as a FV cosine theta. And that can be reconsidered as FV parallel, or that can be considered as F parallel V, where, V cosine theta is V parallel and F cosine theta is F parallel. That's just analogous to what we were doing when we were talking about 3 forms for torque. And that's just something that you can think about as you're using it here. Number 12. In this case, the only thing I need to tell you really is what is conserved. Well, one thing kinetic energy is not, because when you have something dropped on another thing and then they finally slip until they're going at the same speed, you've got heating going on here. Finally, number 13. You go back, review your formula for a physical pendulum, and the thing that this will help you is to remind yourself, what did L sub P and I sub P refer to in that formula? There, I hope that helps.